Okay, so in this section, we're concerned with taking the integrals of rational functions. And I'll start with an example here. The integral of x minus 5 divided by x plus 1 times x plus 4. Now, one way to do this is to multiply out the denominator to x squared plus 5x plus 4, and then completing the square, and this becomes x plus 5 halves squared. So that's 25 over 4, so that's minus 9 over 4 dx. Right? And so the denominator here is in the form x squared minus a squared. Right? Where instead of x, we have a translate of x, but it's the same thing. We can actually use a substitution. X plus 5 halves is equal to 3 halves secant theta. In order to use this trigonometric substitution, now we need to compute dx. 3 halves secant theta, tangent theta, d theta. And as well, we can also compute x plus 5 halves squared minus 9 over 4. This gives me 9 over 4 secant squared theta minus 9 over 4, or simply 9 over 4 tangent squared theta. Right, so it's just your standard trig substitution, where instead of x, it's a translate of x. And so applying this substitution, well, x is now 3 halves secant theta minus 5 halves, and we're dividing by 9 over 4 tangent squared theta. And then dx is this whole expression, 3 halves secant theta, tangent theta, d theta. And you simplify, and then you integrate. Right? But yeah, I don't want to do this. Who wants to do this? Thankfully, there's an easier way of evaluating this integral. And all you really needed to notice here is that the fraction x minus 5 over x plus 1 times x plus 4, right, this rational function, this actually is equal to 3 over x plus 4 minus 2 over x plus 1. Right, and we can check this. Writing your common denominator, x plus 4, x plus 1, right, using your LCD. The top is now 3x plus 3 minus 2x minus 8 all over the denominator we want. And you can check this is x minus 5. Okay, so therefore this integral is just the integral of 3 over x plus 4 minus 2 over x plus 1 dx. Immediately, this tells me this is now 3 ln x plus 4 minus 2 ln x plus 1 plus c. Right, and so compare the two methods that we tried, right? Here, we needed to use secant, right? And then we got an integral with secant and tangent. And we would still need to split that up anyway, right? Because of this minus sign. Here, once we knew what this decomposition is, it was very, very easy, right? It's 1 over a linear function. That's just a logarithm for its antiderivative. And so the question here is, how can we find this in the first place, right? If this indeed makes evaluating these integrals easier, then we would benefit from having a systematic way of doing that. And that is called the partial fraction decomposition of a rational function, right? That's the title of this video. And in general, this is how it works. Remember that a rational function is basically a fraction that involves polynomials, right? So on the top, it's a polynomial. On the bottom, it's also a polynomial. And they're going to have degrees, degree p and degree q, I'll call them. The first step you want to do is to make sure that the degree on top is smaller than the degree on the bottom. Otherwise, if the degree on top is larger, then you want to simplify that first, right? And remove as many copies of q of x as you can. You're able to do so by just simply dividing. Just use long division there. All right, it's the same thing with what we do with numbers. Right? If you had 37 over 5, then you would say, well, let's divide 37 and 5. So we could write 37 over 5 as 7 plus 2 over 5. And 7, that's just a whole number, and now 2 over 5 is just a fractional part. So the fractional part became smaller. That's the idea here with our first step. After we do that, once you get your fraction to a point where the degree on top is at most the degree on the bottom, or no, this is the other way around, it should be at least here, and we want to get our rational function into a place where the degree on top is strictly smaller. Okay, so in this case, the next step is now to factor q. And we know that we will be able to factor q into a combination of linear factors and quadratic factors that are irreducible. Right? And irreducible simply means you can't factor it any further. Something like x squared plus 1. Right? If it's x squared minus 1, then that still would be factorable into x plus 1 times x minus 1. And after you factor q, well, depending on the factors that you have, if you have a linear factor in the denominator, say ax plus b, and suppose you had n copies of that in the denominator, what does that tell us about our partial fraction decomposition? Well, this tells me that my decomposition may have terms of the following form. Ax plus b in the denominator, ax plus b squared, and all the terms until ax plus b to the nth power. Right? And you'll just have numbers on top here, so I can call them a1, a2 up to an. Right? So that's just the most general form that your decomposition may have, because you have that n power term for your linear term in the denominator. Okay. Now, if your fraction has a quadratic term that's irreducible, then it's very similar. You're just going to have to include n copies of these fractions from power 1 to power n in the denominator. But now for the numerator, you have linear terms. a1x plus b1 and then anx plus bn. And so to get your decomposition, really all you have to do is factor q into these linear terms, and then for each of these linear or quadratic terms, you're solving for these values of a1, a2, a1, b1, and so on. Okay, so that's probably a bit abstract for you, right? So let's work on an actual example so I can show you what I mean here. Evaluate this integral, 3x over x squared plus 2x squared plus 2x plus 4. Oh, that's a typo there. That should be x cubed plus 2x squared plus 2x plus 4. Okay, so again, your first step is to make sure that the power on top is, well, the degree on top is smaller than the degree on the bottom. That's already true here. Linear on top, cubic on the bottom. Next step is now to factor. So we factor x cubed plus 2x squared plus 2x plus 4. This is easy enough to factor by grouping here. We factor x squared from the first two terms, and we factor 2 from the last two terms. And then we factor x plus 2 from both terms to get x squared plus 2 times x plus 2. So my integral is just 3x divided by x squared plus 2 times x plus 2 dx. Okay, what does this tell me? Right, so remember from the previous slide, the power n of your terms in the denominator tell you how many we might see in the decomposition, right? We go all the way up to power n in the decomposition. But here the power is just 1 for this irreducible quadratic and the linear term beside it. Therefore, I know that my decomposition is going to be in this form. 3x over x squared plus 2 times x plus 2 is going to be equal to, well, a linear term. I can just call that ax plus b over my irreducible quadratic x squared plus 2, and then c, just a constant number, over x plus 2. Right? And this again follows from the previous slide. And really, you've done the most important step here, right? Once you get the correct form for the decomposition, now you just have to solve for a, b, and c, and you can do that in a couple of ways. First, you can try multiplying both sides by x squared plus 2 times x plus 2. Right? Basically, you're multiplying by the LCD. Another way to think about that is you're using the LCD to write these two terms on the right as one fraction. Right? So how would you do that? This becomes ax plus b times x plus 2 plus c times x squared plus 2. Okay, so you have two fractions here, and we want them to be the same, right, for any value of x. Right, so that's the key in what we're doing here. We're trying to get your fraction here into another form. Really, that's equal to it, right? Which means any value of x I plug in, I should get the same thing on both sides. Well, the denominator is the same here in the equation I came up with, so I can just erase the denominators and just deal with the numerators. Right, so really, I'm looking for a, b, and c so that these left-hand side and right-hand side, they're equal. Right, so I can do this a bunch of ways. The first way is to plug in values for x. For instance, I can plug in x equals 0, and the equation must be true at x equals 0. Therefore, I get 0 equals a times 0 plus b times 0 plus 2 plus c times 0 plus 2. This gives me 2b plus 2c equals 0. All right, and you can kind of see what happens here. You can keep plugging in numbers, and I'm going to get equations that involve only the unknown a, b, and c parameters. Right, so negative 2 I plug in, that's negative 2a plus b. Oh, but negative 2 plus 2 is 0, right? That's why I plugged in negative 2, because this term disappears. So I'm just left with negative 2 squared plus 2, that's 6. So 6c is negative 6, gives me c equals negative 1. And immediately this tells me that b has to be equal to 1. And I can just plug in one last value for x. 3 equals a plus b times 3 plus c times 3. Well, I know b and c are 1 and negative 1. So they'll just basically cancel each other here on the right side, and I'm going to be left with 3a equals b, which means a is equal to 1. And now I know my decomposition, right? I can just plug in a equals 1 here, b equals 1 as well, c equals negative 1. So now my integral is just the integral of, well, this thing. And I can evaluate that much more easily. Right, so what am I going to get there? Well, I'd still have to split up the first fraction into two parts, and then I can use a substitution. Right, so that's going to give me ln of x squared plus 2, well, times 1/2, plus 1 over root 2 tangent inverse x over root 2, and then minus ln absolute value of x plus 2 plus c. Right, so these are just all from your table of definite integrals now. Inverse tangent and logarithm.